on Friday after the exam, and yeah, so we thought we'd mark them and get them back to you as soon as possible. So yeah, the exam was long; it was too long. On the other hand, there was a lot of benefits to having an exam that was that long because, first of all, it actually gave you practice on each of the three sections. So it's the short answers really that that people spent the most time at. But that gave you at least one example for each of those sections, which is actually very important. The second is these multiple choice questions really don't tell us very much. We're looking at the distributions, the correlations between the multiple choice and the short answers, and there's really not a very good correlation. If you had to make an evaluation of who's the top students just by looking at the multiple choice, the chances are that you could be pretty wrong. And if you think about it, for a multiple choice question, you got 4 answers. Usually 2 of them you could throw away pretty readily. So that means that you're really stuck between 2. And even if you knew nothing, then that's a 50-50 chance, and you got 50%. So I'm not overly enamored with short answer questions, or multiple choice questions, but they do provide some information, and they also provide an opportunity to study. So we won't take up the exam today. We're going to take it up when we get a little bit of breathing time, but you've got the lab this afternoon, so there's a few basic things that we really need to kind of get. So that's our goal for today. So if you remember where we were at the end of last lecture, we were looking at electromagnetic induction, and the example that we were using was this guy that was coming through in the security system, and the general sort of physical idea of what's going on is that we've got a transmitter here, so that's giving out a time-varying magnetic field. If that sees something that's conductive in here, it generates currents, and if those currents then generate another magnetic field that's picked up by the sensor. So those are the 3 elements that we have, and we encapsulated it in terms of this. So here's the 5 guys here that are really important, and we're going to go through them today one by one and make sure you've got all of the basic concepts. So the first is that we've got some kind of a transmitter, and usually that's just a loop of wire, and that wire generates a magnetic field. So if you remember that right-hand rule, if we think about a current that's going in this wire, then that magnetic field is going to go like this, and it's actually going to look like a dipole. So if we're sitting any place in here and we see this time-varying magnetic field, then that generates this electric field. So that's that force that is going to cause electrons to move. If their material is conductive, then that gives us an electric current density, J, which is equal to sigma times E, the conductivity. And then those currents produce a secondary magnetic field that we can measure at a receiver. So that's the process, and we're just kind of going to step through. And since you're really all rested up from the weekend, you have the opportunity. This is probably one of the most kind of interesting and challenging mental exercises you'll have in this lecture today, just to kind of keep track of everything. So we're going to take each one of them separately. First of all, we're going to have a transmitter and the primary field. And then we're going to look at something called the magnetic flux and something called coupling. So those are essential elements that we're going to need. Then we'll look at the target, what the induced currents are, secondary fields, what the receiver are, and the data. So we're going to take each of these in turn. So let's look at a generic system. So we've got a transmitter. So as I said, here's just going to be a loop of wire, and we're going to attach a generator to it, and it's going to give a primary field that will propagate into the earth. It could also propagate to a receiver. So this primary field goes everywhere. We're going to have something in here. That's our target. It's going to be inside the earth, or for what we do, we're just going to put it in free space to start with. And then we're going to have a receiver, which is just another coil of wire that will be used. So those are the three elements: transmitter, target, and receiver. So this is something that we should kind of remember. We were talking about the Earth's magnetic field, and how are we thinking about the Earth's magnetic field being generated? Anybody?
Current.
Yeah, so we've got these currents inside the Earth, inside the core. So those currents then give rise to our magnetic field. And if you want to think about in the Earth, you can just think about sort of inside the core. There's just some great big current that's going around, and then the magnetic field at any point is just given by that rule. So if you think about putting your thumb on this current here, you can see how it would sort of curve around, and so you get a magnetic field that looks like that. But because it's sort of, at each point here, it's kind of going around. By the time you do it all the way around, it actually looks something like that, and that's a field that you recognize as being like that of a dipole. So one of the first things is that if we have a loop of current, so current I that's going in here, then the magnetic field looks like this, which was just like a dipole. We can also calculate what the strength of that dipole is. Remember, we had this thing called the magnetic moment. When we translate that to a loop and a current, it's just the area of the loop times whatever the current is. So if we have some particular area here, then the strength of that, or that current multiplied by the area, gives rise to that magnetic moment. So that's actually how we make that correspondence between any kind of current and both the magnetic field and the total strength. So good. So now I've got a magnetic field that looks like this, but I've got a generator that's attached to this, and that generator might be putting out a sinusoidal wave that looks like that. So what that means is that sometimes the current is going this way in the loop, and then it stops, and then it goes this way. So it's alternating, going this way, this way, this way. So you can imagine what that happens to the magnetic field. So if the loop, if the current's flowing this way, then the magnetic field is pointing this way. If current's going the other way, it's pointing that way. So at one point, the current's pointing this way, then that way, this way, that way. So that means that there's a time-varying magnetic field. So that's the ticket. We have a generator here that's got an oscillating current. It generates a time-varying magnetic field, so that now if you're a target body there, then you're going to see this time-varying magnetic field, and that's going to generate currents in you. Okay, so the time-varying current gives a time-varying magnetic field. And you can also see the other thing that happens too is that depending upon the orientation of this, so you can imagine this guy is like a current that's going in here, so I got a dipole. But if I move it this way, then I've got a particular orientation of the dipole. If I move it this way, I've got another orientation. So depending upon the orientation of my loop, I'm actually going to get different magnetic fields wherever I point. So the next thing that we need to do is to quantify something called the magnetic flux. So if I've got a loop, so let's suppose I got a loop. Can you guys see that from there? So I've got a loop that's sort of sitting up here. I've got a primary field that's coming through there. So there's always going to be some magnetic flux that's coming. There's always going to be some magnetic field that's coming through. We can define something called the magnetic flux, which is equal to B, that magnetic field, dot and hat dA, where the integral is over the area of this loop. The dot hat means that it's just the normal component of U. So if I've got something, then if I've got a magnetic field that's coming in like this and is constant, then the flux is just the strength of that magnetic field times the area. But if I move this like this, then I get much less flux that's coming through. And if I move it like this, then I don't have anything that's really penetrating that particular loop. So that means that the flux is equal to 0. So we're trying to show this in this next diagram here. So if I've got a magnetic field that's come like this, and I've got a coil that looks like this, then that normal component of the flux is just one that's straight through. And so the total flux is just equal to the area times whatever H is. But if I orient this a little bit, then I've got a smaller amount of flux. And if I make it like this, then I've got no flux that's coming in through there at all. Okay, so we've got a loop that's a transmitter. It's providing a magnetic flux that goes through here, and the value of that flux depends upon that orientation of this transmitter and this guy here, just to see how all the fields go. Okay? One more thing is that we cared about the time variation of that flux. So we don't just care about this guy, we care about how much it's changing in time. Because the magnetic field that's impinging on you doesn't do anything, just a magnetic field. But if I change that, then it's going to cause some currents to flow. And the thing that is important is that time rate of change of flux in a circuit. It's called the voltage, and that's just equal to this quantity here minus d phi b dt. And this minus sign here, anybody remember where that came from last time? We talked about a guy with particular. Anybody?
The voltage is trying to oppose the change in the first direction.
Right, exactly. So that's what is happening. There was actually a name of a law for that. What was the guy's name? Lenz. So Lenz's law kind of told you how, and that's the thing that tells you how that current, which way that current is going to go. Okay, just to recap slightly. So we've got a coil of wire, gives a magnetic field, just like a dipole. Then depending upon where your target is and how the target is coupled with these fields, then you get places that the target is not coupled, so the magnetic field is kind of going, parallel to the plane of the. So here the magnetic field is coming down here. There's nothing that's cutting it. Whereas if you're sitting up here, then you've got full force that's coming. So now you've got really a highly coupled system. So when you're sitting in these locations here, you're actually going to have a lot of currents that are going to be generated because you're going to be really well coupled. Okay. Good. So these time-varying fields on here are going to give rise to currents that are going to go in this body. And now what we want to do is to take a little bit of look at those currents and then see what the magnetic fields are that are going to be generated at the receiver. So that receiver is just, you can just think about it as another coil that's sitting up there. And there's two, well, maybe I can go to the back one. The transmitter gives rise to this field that comes out here. Part of it goes onto the body, but there could actually be something that is measured here at the receiver. And what we're going to do, we're going to subtract this primary field at the receiver. So we're only going to be looking at what the secondary field is. That's the field from here at the receiver. And the quantity that we're going to be interested in is how much the secondary field is due to this target compared to what the primary field is. So we're going to be looking at a datum that looks like this. So our instrument's going to measure the secondary field divided by whatever the primary is. So now what we want to do is we're going to take this in two parts. We're going to first of all kind of sketch what the nature of the fields are going to be. And the thing that I'd like you to kind of keep in mind is the idea that we're going to have a system. The one that we're going to use is something called an EM31, and it's basically a rod, and it's got a transmitting coil on one side, and it's got a receiving coil on the other. And you're going to take this guy, and you're just going to walk along with it. And if it happens that there's a a pipe or plate or something here, you're going to get a particular characteristic signature that goes with that. And that characteristic signature is one that looks like this. So here's our pipe. And the signature as you walk along like this is going to be something then that looks like this. So what we're looking at here is our data. That's that HS to HP. And it's going to have some signature that looks like this, and it's going to be sort of a maximum right over the pipe. So what I want to try to explain today is why we get this kind of signature. And the reason I do that is if you can understand at the end of this lecture why when we take this particular instrument over a pipe or a rod or something like that, and we get out something like this, then you really will have understood all of the essential ingredients with respect to electromagnetic induction, or at least a lot of them. So that's our game plan. So there's going to be a few things you've got to pay real close attention to what's going on. And I'm not sure which blackboard is the best to write on in this case. Can you guys see that one at all? So what we're going to do is to look at a case like this. We've got a buried pipe, and we're going to have a system like this EM31 that I just talked about, and it's going to go over top of here, and we're going to try to sketch out the fields. And we're going to end up with something that looks like this. It's going to have a positive on one side. It's going to have a big negative over here with a maximum being at the location of the pipe, and then another positive. So we're going to try to figure out how that sketch works and why it's being plotted as it is. So first of all, we've got our transmitter. And that transmitter, so that I suppose there's a current that's going to flow in that direction, then that's going to give rise to a primary magnetic field, right? So if it's like this, okay, then if the current is going this way, then we get a primary field that looks like this, right? So it's that magnetic field that we had talked about. If we now put on a target in here, so let's make another one here. So here's our transmitter, and here's our target. So it's a plate, or some plate's a little bit easier to think about. So imagine we've got a vertical plate, and now we've got a magnetic field that's coming in like this. Right, so here's our primary field. And you notice that this primary field is coming into the plate. Okay, so if that primary field is coming into the plate, then which way is the current going to flow in the plate? So now you can imagine the plate's like this. The primary field is coming in like this. And so there's going to be a current that's going to be set up in this plate. It's either going to go this way or it's going to go this way. So which way is the current going to flow?
To the ward.
So we've got to oppose this. So here is the current going to go in or out? It's going to come out. So our current's going to be coming out here and in, right? And so now when I do that, got my right-hand rule. So now my secondary field is coming out like this. So if I just drew the secondary field, then my secondary field is kind of coming out like that. Yeah?
Sorry, why do we have to oppose that?
That's Lenz's law.
Oh.
Right? So if I think about a magnetic field that's coming in, and we're assuming it's increasing, then I've got to have a current that makes a magnetic field that opposes that. So remember when we did the little magnet in the coil, and we shoved the magnet in? When we shoved it in, the voltage went one way, we shoved it out, or pulled it out, went the other way. So all of that tells you, okay, which way is it's going in. And nature, for some reason, loves to not have any things change. So if you change the magnetic field, then it's going to work in opposition. So that's the ticket for understanding which way this guy goes. Okay, so here's now the secondary field that looks like this. Okay, so as long as my transmitter, so suppose my transmitter is sitting to this side of the plate. Okay. If I now look to see which way so my datum is HS over HP. And if you notice, I'm plotting it as positive and negative. So there's a question, okay. What's my sign convention about positives and negatives? My sign convention is going to be the following. If HS is in the same direction as HP, then I'm going to say it's positive. Okay? That's my convention. I get to choose. So now let's look at the situation that I've just drawn. If I've got a transmitter over here, then my primary field is coming down. Okay? So my primary field is like this. So now let's suppose I've got a receiver that's sitting up over here. Primary field's down. And now my plate, look at my plate. If I'm sitting over here, my magnetic field the secondary field is also coming down. So my secondary field from the plate is also coming down. So my primary field and the secondary field are going to be in the same direction on this side. And that means that if I try to just sketch things out, that if I'm sitting over here with both transmitter and receiver on one side of the plate, if I draw it in a bit smaller scale, then I'm going to be sitting here with some kind of a positive number. Okay, so that accounts for this part over here. Okay, so far so good? Okay, now what's going to happen? I'm going to walk, and then there's going to be a place where my receiver coil is actually going to be sitting right above the plate. So why would we care about that? Suppose, so I've still got my transmitter over here. Suppose that my receiver was sitting right here. Then what would the value of the datum be?
0.
It would be 0, correct. And why?
It's the primary field is no longer coupled with the coil.
The primary field's coupled. Secondary fields,
Okay.
right? So this field here, right, from here, is like this. So if that's my receiver coil, then my magnetic field lines are like this. So I got no flux. That means there's got to be a 0 crossing at some particular location, in which, and that's the location at which the receiver was sitting right up over top here. So that gives us this point here. Now what happens when the transmitter is over on this side, but my receiver is over here? Well, when the receiver is over here on this side, then my secondary magnetic field is up. My primary field was down, so they're going to be opposite direction. So that means that this is now going to be a large negative value. Okay. As I keep coming over, I'm going to actually hit a spot in which my transmitter is sitting right above the plate. What is going to be the value of the datum when my transmitter is right above the plate? Going to be 0, correct, and why? You're halfway there. Got the right answer. Why is it going to be 0? Right. So now it's a different kind of kettle of fish. I've got a plate here, and I got a transmitter that's got a magnetic field that's going like this. There's no EMF that's produced in here. There's no flux that's going through there, so I don't have any signal. So there's no currents. That gives rise to another 0. And then later on, when they're both on the same side of the plate, they look like this. So here is my final picture. There was a lot of stuff that went into here. And so it's going to take you, you're going to have to sort of sort through this a couple of times before you really kind of crystallize it. But the idea is kind of recap. So here's actually the EM31. I will bring one in, and you can take a look at it. The transmitting coil is about 10,000 hertz, and this is the same one that we used on the expo site. I showed you those data right at the beginning of this, and you'll see them later on because we're going to go over and see if we can't find that contaminated oil spill and some wires and stuff like this. So here's the thing. It's about 3.5 meters long. When both the transmitter and the receiver are on one side, then the secondary, we get current, when the transmitter's on this side, we get currents that are going in one direction in this plate. And when the receiver's here, then the primary and the secondary field are in the same direction. As the instrument gets over top so that the receiver is sitting right over here, then we have a 0. A little bit later, when I got the receiver on one, or transmitter on one side and the receiver on the other, then I get a very large signal that these are in opposite directions. So I'm going to have a big negative. So now I'm sitting right here. And then I come across, now I got another 0 crossings, but it's an entirely different physical basis. This guy is got a 0 because there's no currents that are being developed in here. So I got 2 0 crossings. The first one, because it's null coupled, there's actually signal there, but my coil is not oriented in the right direction to see anything. And this one is 0 because there's just no currents being generated. And then everything is on. Okay? So that's the sketch of the signal. And as we go through, and over the next sort of week or so, you're going to become more familiar with kind of what's going on physically here. And you can expect probably on the final exam, I'll ask you some kind of scenario that's somehow related to this. So it's going to be, you're going to be thinking about a transmitter, which way the primary fields are going, which way the currents are going, which way the secondary fields are going, and then to kind of sketch those things. Because the thing about this is not so much understanding, like, okay, a tight curve should look like this, because if I change the instrument a little bit, they won't look like this. But the point is, if you can actually talk your way through this, and you see that it's a lot of stuff that's going on physically. If you can actually talk your way through this and come up with the right shape, then you understand it. So it's the same kind of thing that we had when we did the magnetics, right? So that if you could bury something at different parts of the Earth and decide you're going to do this component or that component, like you're good to go. You understand what's going on, and that's the point. Okay, so we've got the basic element down here. We've got fluxes. We've got all our geometries. Remember when I first showed you the data, actually from the expo side, I showed you 2 images, and I said, well, one was the real part and the other was the imaginary part. So what is that? Now, my understanding is that if I wrote I is equal to the square root of -1, how many people would know what that is? Half. And if I wrote e to the I omega t, how many people would know how to expand that? What is it?
Cos omega t plus, I think, I size.
Perfect. So when we deal with electromagnetics, we actually deal with a lot of systems. Mathematically, it turns out to be easier to couch the mathematics in terms of what's called complex numbers, which involve the square root of -1, and to write things in this complex notation. So we're not going to go there, but the reason that things come up like this is that if we take something like this and we write this in terms of in this form here, we often refer to this guy here as being the real part, and then because there's an I in here, we call this part the imaginary part. So there's kind of two parts that are going on. So the data are complex, but the understanding of the data is actually not so difficult because what that complex value does is kind of turn things into what's called a phase lag. So let me try to explain this. So suppose I've got a sinusoid that's going. So I got a transmitter that's going like this, right? Remember? So it's oscillating. Then everything in the field of that transmitter oscillates with that same frequency. So if the frequency, you know, is like 10,000 hertz or 1,000 hertz, then and omega is 2 pi f. So omega is angular frequency. So 2 pi times. So this is in hertz. This is angular frequency. Okay. So if I've got a transmitter that's operating at some particular frequency, and there's something that happens inside the Earth, we get currents, we get magnetic fields, anything that come back, that has to oscillate at the same frequency. So when I'm receiving something, I'm measuring something that's happening at the same frequency, and the only information I can get 2 pieces of information. Anybody suggest what they might be? For me, I can have an amplitude. So if if you're there being the source of some harmonic frequency, it could be an amplitude, and the other thing, it could be a phase. So here's my transmitter. It's got an amplitude that looks like this, right? And then I measure a voltage, and that voltage is also sinusoidal. So it's got some amplitude, so that's important. But the other thing is that it's phase shifted. So when this hits a maximum, so at the time that this hits a maximum, which is there, this guy, you know, is not at a maximum. He's shifted a little bit, and that phase shift here, psi, denotes how much. Well, denotes how much these things differ in phase. Okay, so what I'm going to measure, okay, is some wave. It's got an amplitude, and if I'm going to represent my time variation, it's going to have like a cosine omega t plus some kind of phase, right? So the thing I'm going to measure is going to be looking like this, but this now you have seen before, and you can take this and you can break that into 2 parts, right? So the cosine omega t plus psi goes to cosine omega t cos psi minus sine omega t sine psi. Right? Remember? So cosine omega t plus some constant goes to, you know, a cosine omega t. That's the first term, and then a cosine of psi, and then a minus the sine omega t sine psi. So if there's some amplitude in here, amplitude, there we have an amplitude, and here we have an amplitude. So let's combine those things. So let's take this guy and this guy. So that gives us an A cosine of psi times cosine omega t minus A sine of psi sine omega t. So what does this mean? Okay, so my primary wave is that he's cosine omega t, so he's going like this, right? And now I've got something that's coming back, and I can decompose it into 2 parts. Part of it is in phase. I can never do this. Okay, so I've got this amplitude here, and I've got this guy here. He's coming along. He's the same phase, but just has different amplitude. Okay? So that's what this first part is. This is telling us for when something is coming back, how much, what portion of that that's coming back is in phase with the primary. Okay. This guy tells us how much is out of phase, right? So if he's coming down like this, okay, so that's these guys, right? Okay, now I want to make this amplitude small, right? You got it. All right, so you got it. So there's a certain amount that's in phase, and then there's a certain amount that's out of phase. The in phase part, we give different names to it. Sometimes we call it the real part. Sometimes we call it the in phase part. Two names mean the same thing, and you'll see this all the way through the literature. So this part here is sometimes called the real part, and it's sometimes called the in phase. This part is sometimes called the out of phase, is sometimes called quadrature, and is sometimes called the imaginary. Historically, all of those are used interchangeably, and you just kind of get used to it. These are three words all mean exactly the same thing. Here's two words that all mean exactly the same thing. So now we go back to our data. So we've got a primary field. So we got a primary field that's H sub P for primary, co-solving T, right? So that tells us how that one's oscillating. And then we got a secondary field that looks the same HS, so it's a different amplitude, but it's got a cosine omega T plus psi, so different phase shift. So if we carry this guy out and we do that separation, we get something like this. And then we're going to divide it by whatever the primary field was, the HP. And we get this guy here. So we've got this part that's the in phase, a part that's out of phase. And the in phase is then just given by this quantity and the out of phase by that. Okay, so we're actually making huge progress. This is a lot of stuff today. Okay, so we've got the whole concept of inducing currents and getting the secondary fields back, and now it's that ratio of the secondary to the primary that's going to be important, but because of how the waves come back, there's going to be a certain part that's in phase and a certain part that's out of phase. The last thing, and then we can rest your minds, is to try to figure out what portion goes into this in phase and what portion goes into the out of phase, and how all of that kind of relates to those data that you have. And the crux of it is that if you have a target, and we'll work with it, what you're going to do in the lab is you're going to have a transmitter, and you're going to have a target, and then you're going to have a receiver. This target is just a loop. It's just a loop of wire. And from circuit analysis, if you guys do circuit analysis, right? So you got a battery, and then what are the components that we could have in a circuit? A resistor, good. Anything else? You could have a capacitor. Anything else? And we could have an inductor. Okay, the inductor is L, resistance is R, and actually we don't have to worry about the capacitor. Makes it easy. So we're going to represent our circuit, our target, in terms of kind of resistors and inductors. In the GPG, there's a little bit of explanation about how we get there, and I might go back and talk a bit more. But for now, I just want to kind of get the overall concept and get the picture, because you're going to be seeing this picture this afternoon. So I want to get you there. This phase shift is equal to, first of all, pi by 2. And then there's another term in here, which is the arctangent of omega L upon R. Omega is the frequency, L is the inductance, and R is the resistance. Okay, so you can think about your target as being a circuit, and it's just got this L here and an R. And the thing about this is that if R gets to be really large, so let's suppose you got a really big resistor. So imagine in the ground, you know, there's just no conductor there whatsoever. Okay, so the resistance just goes to infinity. Then if R goes to infinity, what is this? Guys, remember what arctan of? Well, actually, if R goes to infinity, what is this argument in here? 0. Arctan of 0 is? Zero. Okay. Remember the tangent function? Oh, it was a long time ago, wasn't it? All right. All right. Okay, so the tangent, so that gives you 0. So then this just goes to pi by 2. So if R goes to infinity, then psi, this phase shift, is just pi by 2. If L gets to be really, well, actually, if omega, the frequency, goes to 0, that's another way of making this quantity equal to 0, right? So we can either make R very large or omega very small. And in both of those cases, the arctan goes to 0, and so everything goes to just pi by 2. Okay? If R, however, happens to go to 0, then what happens to this guy? Infinity. And if that goes to infinity, this guy is pi by 2. Pi by 2 plus pi by 2 is equal to pi. And hence, we've got two sort of n members. The in-phase part and the out-of-phase part then get plotted up in the following manner because of this, because it progressively shifts. And there's a picture that we'll be dealing with in which this axis here is the product effectively of omega times sigma, or omega divided by R, the resistance. So as we get higher up into frequency, so this is you can basically think like this is a good conductor, really high frequency, good conductor over here, and in that case, the phase shift gets up to be pi by 2, and we end up at something called the inductive limit here, where everything is in the real part. And when we have very low frequencies or poor conductors, we end up with the real parts like this. And this out of phase part has this kind of a signature that's attached to it. So the details about exactly how this comes to being, I think, is not so important as just kind of getting a sense of what the response of that conductor is. And these two parts here, the imaginary, the out of phase part, and the real part behaving something like this. So as you get to have really good conductors, virtually all of the information is in that real part. When you have intermediate conductors, there's information both in the out of phase part and in the real. And when you have really poor conductors, most of the information is in that out of phase part. So how does this translate back into the following? So we've worked and we've got this iconic diagram here. So here we're bringing the EM31 over top of that pipe. Okay, we've kind of figured out how to do that. It's just that now we've got one more detail to think about, and that is that actually, although that's the shape, when we obtain something, we've actually got two numbers, a real and imaginary part. How do we know which is which or what the other one looks like? So let's suppose that this is the real part here. If we look at this particular diagram, and if we've got a really big conductor, okay, so we're over here, then the real part's much bigger than the imaginary part, and hence the signal that we should see, if that's the real part, then the imaginary, it'll have the same shape, but it'll be really smaller amplitude. So both things will have the same shape, but the amplitude of one versus the other depends upon whether you've got a big conductor or a small conductor. So in the cases where you've got a really large conductor, as we'll see when we have pipes, then most of the information is actually going to be in the real part, and the signature is going to look something like this. On the other hand, if we go to something that's got a much smaller conductivity, then these things could be reversed. The real part could look like this, and the imaginary part. Okay. So where you're going to go this afternoon in the lab, you're going to have an app, and you're going to have a circuit model, and you're going to kind of wend your way through the drawing of that kind of characteristic curve. And then there's going to be a question about, okay, if you've got a big conductor or a small conductor, you know, which of these guys is bigger? So you'll be able to kind of basically review all of the stuff that we. So that was good. You guys deserve a gold star. That was probably more stuff than we've had in any particular lecture. Good. Thanks.